Sorry, I'm a software guy and the hardware things, thank you again, sometimes trip me up. So disregard that previous picture. It was me in that most cursed mode called marketing mode, which I kind of despise. This is the real me. And there is my email address. It's not a fake one. So if you have questions on this talk, later or whenever, please, by all means, mail me, and I'll do the best I can to answer them. So I have a number of presentation styles. Luckily or unluckily for you, it's Wednesday, which means Microsoft PowerPoint. Really, I'm much better in Mongolian throat singing, but you'll have to do with PowerPoint. I will try and not put you guys to sleep with 423 PowerPoint slides, rather try and do something more interesting. So, motivation. This is a block diagram of a traditional operational support system in the telco world. A business support system actually probably looks just as bad or worse. By operational support system, I mean functionality like configuration management, inventory management, service provisioning. By business support system, I mean things like billing, customer care, customer retention. And normally I would be walking around the stage, but proving the inner geek in me is still alive and kicking, I kind of forgot my glasses. Humorous story, I call my wife and says, I forgot my glasses, and she says, you moron. Thank you very much, Kim. And of course, I turn to support to my dear friends Alva Couch and Mark Burgess, and of course, they say, stop right there, John, your wife's right. So I think I'll just kind of stay here so I don't trip on anything. And if you look at this picture, forget all the lines. I mean, it kind of looks like a circuit schematic. But notice that there's groups of these boxes of a similar color, which, of course, I also cannot see because I forgot my glasses. But I think there's like blue and red and things like that. Do you know why that is? That's not me, I hope. Is that me? Thank you. The reason that these are color-coded Testing, sibilance. Yay, okay. Doesn't take much to make me happy, so. So if you look at this, you see that there's a number of these boxes that are in different colors. Why is that? I've got feedback. Okay. Better? It's going to be a long keynote, but okay. So the reason that these boxes okay. How's that? Better? Full speed ahead? Close enough. So, for the 17th time, the reason that we've got different colored boxes in this slide is because each color corresponds to a group of admins that are responsible for that. Thank you. Thank you. Yes, yes. I thought we already were. Okay.
John, go ahead, grab the original lavalier that you had. Grab the original mic that you had.
I could say that I rehearsed this, but actually I didn't. Okay? Okay. Just a tiny bit paranoid at this point. So each of these colors correspond to a particular set of admins that are responsible for that function or functions. That should be frightening to you all, right? I mean, you wonder how come it takes, so long for a fairly trivial service like DSL to be put in. Well, this is one of the reasons, right? There isn't a single admin or even group of admins that knows how this OSS works. And by the way, this is a real OSS from a Tier 1 service provider, name withheld to protect the guilty. So what happened? Why was it that bad? Well, if I look at inventory management here, the service provider or enterprise will usually pick the business application or configuration application that's best in breed. I mean, that kind of makes sense, right? Why would you want, a bad one when you can get a good one? Problem with that is that each of these best of breed applications view data microscopically, just for their own purposes. And so if I look at the nature of an operational or business support system, which has lots of different of these best of breed applications, like config management, service order management, et cetera, each one of them has its own database, its own view of what should be common management data. And so in the telco world, we call this the stovepipe syndrome. And it's a problem because if, for example, the first one, inventory management, has two keys, John S. and a customer ID of 12345 as a number, and the second one has those same two keys, but the name is Strassner.John, and the ID is a string 12345, Houston, we got a problem, because it's probably unlikely on a Tier 1 service provider with hundreds of thousands or millions of subscribers that I'm the only subscriber whose first name is a John and last name starts with an S. So how does the computer know that John S. is the same as Strassner.John? And then, of course, we get to the second attribute, which is much worse. Yeah, I've changed the attribute name, I've changed the data type, and these are simple examples of the mess going on. Usually, in a telco operational support system, there is more software and middleware that's written to glue all these together than there is actual code in the best-of-breed applications. In network management, there's lots of problems. Here are four which I think are subtle but really bite you in the derriere, shall we say. So the first is that I might model an individual element, except that when I put groups of those same elements together, their aggregate behavior is different than what I expected. If I'm looking for a cause of a problem, right now the state of the art is basically statistics and rudimentary correlation. Inference and reasoning is few and far between and definitely the exception. And as a result of that, this third bullet is saying that there's really no ability for the current system to go beyond what it already knows. Well, I mean, I came from Cisco. I worked in Cisco iOS, and I'll probably forget more about iOS than a lot of you will ever learn. Trust me, you're better off. But there's no way that I can completely model a Cisco device correctly today. It's too complicated. How do I model the bugs, the side effects, the interaction with other devices, on and on and on. I can write a good model, but it's going to be, by definition, partial. And so what this bullet is saying is, if all I can do is diagnose and debug the little things that I know instead of the much larger things that I don't know, we got a problem. And now the fourth bullet is something that's common to these three. In each of these cases, we require a human in the loop, okay? But yet there's more problems. And by constituency separation, that was, I guess I slipped into professorial mode. Don't throw tomatoes. What I mean there is that when people work on a product or a network, right, they're going to have different backgrounds, different skill sets. I'm going to have the business people that are going to be responsible for how the product works, that's revenue. I'm going to have the system and network architecture people, the programmers, the technicians, the field people. All of these speak different languages. So if I say SLA, or service level agreement, to a business person, they think money, contract revenue, and obligations from a contract, and God forbid, money that they have to reimburse to the customer. Well, if I go down into the data center or the network operations center and say SLA, I'm either going to get SL what? Or I'm going to say, I don't care about all this business speak. I want to, program in CLI or program in SNMP or program in CF Engine. I don't want to hear about revenue and things like that. Well, both of them are right, but what we have to do is actually build a continuum to enable one to speak to the other. And this is a big problem. If you look at this chart, for example, in telecommunications, it is $2,066,245 of revenue per hour that is lost when there's a problem. That's kind of a bad thing. So, what is autonomics? The best thing to do is to introduce it by sound. So, those on the terrified side will claim that the future vision of autonomics is something where machines take over all management tasks, they boot the humans out of the data center or the NOC, or probably just eat them.
I'm sorry, Dave. I'm afraid I can't do that.
Which, of course, is from HAL 9000, where the computer says, you know what, I know better than you, go away. But I like to think of the future vision as a vision where software is actually working for the administrator, doing a lot of manual, boring, time-consuming tasks, compiling information and filtering it so that the administrators can be better leveraged, such as,
Function will require 2 hours to complete. Make it so.
which is actually really cool if you think about it, right? Good old Jean-Luc is saying, I want to do some very, very complex thing, and the autonomic system, of course they had autonomics in Star Trek, thinks about it for a minute and says, okay, I can do that, here's your cost. Do you want to do it or not? And that last part, do you want to do it or not, is actually the key in autonomics. Autonomics is not about replacing people. It's about giving people better services, better information, so that those people can do their jobs better. Ixnay on the sound day for about, I don't know, 100 slides or so. Just kidding on the 100 slides. So pictorially, autonomic networking was announced in 2001 by Paul Horn of IBM. And IBM invited comparison to biology. On the left here, you see a brilliantly drawn picture of a human. On the right is what I do, UML models. And they're both kind of complicated, right? So in biology, the autonomic nervous system is that part of the body that works involuntarily. Like, for example, forgetting my glasses, or putting one foot in front of the other, or raising my heartbeat when I see chocolate so that I can run faster, or any of these other critical things, so that it frees my big brain to do more interesting things. Well, wouldn't it be nice if we could apply this to systems and networks, so that the involuntary functions, such as configuration management or inventory or whatever, could be done, freeing the time of the system and network administrators to do much harder things like capacity management or network optimization or blah, blah, blah. That's the basic idea. A lot of people define autonomics as what I would say self-chop, self-configuration, healing, optimization, and protection. I guess I would beg to differ. Those are benefits. Those aren't a definition. The real importance about autonomics is, how do I get this cool self-star functionality? Well, it starts with knowledge. We need a new way to represent knowledge, so that knowledge from different data sources, maybe pressure-sensitive floors, RFIDs, SNMP commands, heat sensors, etc., can all be harmonized and related to form the context that you're working in. As we'll see, in autonomics, what we want to do is to be able to optimize the services provided as context changes, but optimize those services in a way that are governed by business rules. So in order to do that, we need to learn and reason. We need to link business functions to network functions. Simple example, in comes an SNMP critical alarm, usually a bad thing. The business guy says, that's nice. Which SLAs of which customer are affected? And the network admins like me go, duh, get back to you in about half an hour. Because SNMP doesn't know anything about customers or SLAs or, things like that. So we need to be able to, again, bridge those concepts. It's not about throwing out all your equipment or forcing vendors to retool, because they're not going to retool. There's no reason for them to retool. It's about us getting smarter. And so the most important thing, and I've said this a couple times, but I'll say it one last time, autonomics is really a partnership. And the partnership that I envision is one in which the people and the autonomic systems work together. First kind of, hands off, then they start getting a little closer when the humans start trusting the autonomic systems more, when the autonomic systems prove to the humans that, they can automate this task and they won't screw it up. And that will keep on coming closer. Hopefully we'll never get to the HAL 9000 syndrome. I mean, first of all, I don't think we're smart enough to build software to replace people. And thank you. and secondly, you know, there's things in the network and system administration world that are just too complex. I mean, I'm kind of a smart guy. I'm a good software engineer and architect. I don't have a clue how to write software to do that. You want the human in the loop, okay? And so again, it's this partnership based upon trust that I think is key to autonomics. This, you'll all get slides, so please don't try and read it. God knows I can't. This is a slide from China NetCon that is given courtesy of my friends at IBM, and basically using autonomics products embedded into shipping commercial off-the-shelf products. I think they used Tivoli, for example. They were able to start automating some simple configuration management things. And then, you know, the usual marketing stuff, saved billions of dollars and blah, blah, blah. So, what actually is autonomic networking? Most important thing, if you just want one takeaway, it's a self-governing system. Not a self-managing one, a self-governing one. A self-managing one means I write a bunch of policies, I install them into the device, and I hope against hope that no matter what happens, what type of traffic comes into the device, what types of environmental conditions happen, DDoS attacks or whatever, that those policies will give me the right result. Well, I'm not that smart. So what we want to do then is build a self-governing system where the system actually learns about the environment, and it learns, most importantly, from the administrators that are using it. So for example, if I've got an autonomic system running mobile phones for, let's say, you know, public safety, it starts learning how operators handle calls, and it can then make that decision for the operators, thus speeding up things. From a technical point of view, it's about control loops, closed ones obviously, and how to make those control loops adaptive through machine learning and reasoning, which I'll talk about later. This slide shows something that we in Motorola call seamless mobility. Seamless mobility is any data over any media, over any device, anytime you want it. And I've also got a bridge to sell. But at least that is the vision, okay? And in order to, if you think about that, if you look at this picture, this is really hard. I mean, I've got 2G, 2.5G, 3G, 4G systems. That's just the mobiles floating around. I've got wired networks. I've got, you know, cable. I've got different types of networks, whether they're personal networks or LANs or WANs or whatever. And that makes a really complex system. Complex not just from the technical point of view, right? Me handing over from, let's say, a cellular channel to a Wi-Fi channel to get better bandwidth, but also from a business point of view. When I do that, how does a service provider get money, right? So managing this complexity requires a paradigm shift, which is also what autonomics is about. And we had a, let's see, I guess rather entertaining discussion in a workshop on Monday about what autonomics was. And my thinking actually altered significantly as a result of that. So thanks to you all here at USENIX Lisa. And we in the room collectively agreed that rather than try and describe different types of autonomic systems, forget all that. what we really want to concentrate on is autonomic behaviors, because the behavior of autonomic components, devices, and systems is significantly different if I'm talking about autonomic work inside the device or system, or between systems, or at an even higher level, like at a network or a business process. So how do we make something autonomic? Well, we start with your average everyday device. Could be a server, could be a router or a router for our friends across the pond. And we want to build a management facade, brilliantly called Autonomic Manager, that offers a standard set of APIs that doesn't change what's inside our server or router or router, but rather enables or makes it appear to the outside world that that server, router, or router is indeed operating in an autonomic fashion. But the big problem in doing that is that the managed resource is going to talk in a vendor-specific way. In my world, it's usually SNMP or a vendor-specific command line interface like Cisco iOS. And the Autonomic Manager clearly wants to talk in a vendor-neutral way. Or else it has to learn every single language and every single dialect of that language for every single device out there. That doesn't scale. So how do we do this? We put in a thing called the MBTL, the Model-Based Translation Layer, which I'll show in a minute, well actually in the next slide, does that translation from vendor-specific language and management data to vendor-neutral, so that the Autonomic Manager, which is conceptually drawn inside here, can exert its autonomicity, I think that's a word, well if it isn't a word, it's a word now, upon that managed resource. And so the facade then is that I end up with this block, this building block called an autonomic computing element, and that element appears to the outside world as a fully autonomic thingy, whereas in reality, the managed resource hasn't changed. We've just enveloped it in a management facade. I don't have my Star Wars lightsaber, but I could point at the screen. That'd be easy for you guys to follow. There actually is a loop here. There is a, what? I'm getting rescued. Bless you, thank you. And of course, now I can't see if I'm actually pointing. Is that, yeah? Yeah, hey, let's hear it for the blind guy. Well, come on. Gee. Thank you, thank you, thank you. Okay, so here we've got observe. So as the data is coming in, it gets converted, it's observed, right? And so we analyze that. We might correlate things, or we might just let the raw data pass through. We're then going to compare that data. We're going to do that comparison by determining what its actual running state is, comparing it to its desired state, and if they're the same, we say yay, hooray, and we do it again. And if they're not the same, we go, crap, and we act upon that. We build a reconfiguration command. Now, the cool thing is that there's this bus here, which means that everything can talk to everything. So down at the bottom, you see learn and reason, which means that these are processes that are running in the background. They're continually learning, they're continually reasoning about data, and therefore they can interrupt the control loop to do something hopefully more intelligent. At the top, you see context-aware policy and the foundation, which is the finite state machine. So focal which is the architecture that I've written extensively about, is foundation, observe, compare, act, learn, and then with a little bit of poetic license, reason. So, in real life, here's the model-based translation layer. SNMP and CLI are two ways of getting management information. And what you see on the left here are two repositories. And these basically give us information templates, okay? So here's the managed device, vendor-specific data changed into normalized data, and as an example, SNMP is going to represent this as a set of OIDs, whereas CLI is going to represent this as a Pidgin English type of text, right? So the autonomic manager is going to look at this data, figure out what it means based on these models, and then issue the appropriate command translated back here to the device. Make sense? Kind of? Okay. So this maybe sounds cool. It certainly sounds hard. What the heck are we doing about it? So here's some work in my lab, and also my lab works with a number of universities and other corporations. This is the focal architectural vision. We start with context. So we take a number of different sensors, we harmonize them, we add water and stir and say, okay, this is your current environment. Based on that current environment, we're going to select one or more applicable policies. So if I have a business profile versus a home profile, and I switch, I don't want my business policies applying to my home policies and vice versa. These policies tell the autonomic manager how to change the functions in this control loop. So here we've got the managed resource. It admits data. We normalize it and analyze it, compare the current state to the desired state. If they're the same, we do it again. If not, we reconfigure, and that actually spawns a whole new control loop. That is the vision. It's been published in a number of conference papers. At the end of this, in the notes, you've got a ton of references. So now I'm going to talk about how we've implemented that. We called it Genesis, and it has three main features: a dynamic federation of knowledge bases. So knowledge bases aren't static. They can actually grow or shrink if we found out that they have bad information. And we can federate them together to gain knowledge. We have a number of what we call model transformation engines, which are ways to go from one abstraction or representation to another. And we have this adaptive control loop. You take all of those together, and that's what enables us to build autonomic applications and services. This is a block diagram of it. Now this is going to be fun. Let's see. So on this side, we have a set of agents. In the telco world, they'll call it sensors and effectors. Sensors are ways to get information. Effectors, of course, set that information. In the middle here, we have a set of core services: configuration management, fault management, security management, etc. And then autonomic applications, for example, trend analysis or service provisioning. On this side, this is just console session management presented in a dashboard. If we have time, I can play a flash demo to prove to you guys that this actually was built. It is real hardware and software. And then at the bottom down here, we have a number of different knowledge bases. We've got policies, we've got ontologies, we've got lots of other things. This is the implementation that we have here. Basically, up here, we have a GUI system that's running as a web service using AJAX and a TIBCO messaging bus, although it can also use JMS. There's a GUI backend that does caching and processing, and that's tied into a cache database. That's a so-called object relational database. We wanted an object relational database because with all the models, we deal in a lot of objects that are out here, and this way we can keep that object-oriented paradigm, but also enable, you know, a SQL-like view of the world. And then here, these are execution engines. So for example, we have key performance indicators and key quality indicators. So a key quality indicator might be number of calls dropped, you know, per time unit, and a key performance indicator is lower level than that. So why was the call dropped? What's the signal to noise ratio? Blah, blah, blah. And then this is all built as a set of enterprise Java beans in a JEE application server. We've got JBoss and JRules doing some of the learning and reasoning. And then this front end here is a set of sensors that we can actually spawn dynamically. So if all of a sudden we start getting a lot of data, no big deal. We just clone another sensor and apply that. The cool thing is that all this runs in an IBM Blade server, and we do a whole lot of processing in here due to this architecture. We can handle an entire small city like Cincinnati with just 2 blades, approximate cost $60,000. Not so bad. That all worked because of our emphasis on tools. So first and foremost, we're not going to automate nothing if we don't have the tools to take big tasks apart and work on them in little bits and then reassemble them. So autonomics is not about building one big monolithic system, right? Shame on anyone for doing that, right? Instead, it's about building lots of little systems that are really, really good at doing 1 or maybe 2 specific things, and then we start putting them together to do more complex things. And we do that using a set of tools here, and these tools enable us not only to reuse the objects and behaviors that we build, but we also get to reuse the tools themselves to change, to repurpose our platform to do different types of applications. Autonomics must, and let me repeat, must embrace legacy models, legacy applications, either stuff that was built a long time ago or stuff that's being built today. It's not just about waiting for the new, cool, clean slate approaches, because you know what? Companies like British Telecom have 147,000 routers in their core, estimated cost a whole lot of pounds, probably in the billions. They're not going to throw them away just because some new fancy schmancy gizmo comes out, right? And so what we do is a part of one of my labs is actually working on taking a base system, extracting code, building in parallel the self-star functionality that we want, and then integrating that into the base code to give us that autonomic facade that I was talking about. And this is done in essentially 4 steps. At the meta model level, the meta model is, of course, a model about a model. So it's the thing that allows me to define classes and attributes and other building blocks for me to represent a system. And so as I look at different systems, then I add or delete things in the meta model to enable me to build a model to extract that code, which is down here. Once I've extracted the code, then I can integrate it with my Autonomic software. This is a simplified UML model of a high-level overview of a self-star model, and it's probably too small to be seen. So if you're interested in it, hunt me down. Don't shoot me, though, and I'll be happy to go through it with you later. Once we have the UML model of the self-star model and a extracted UML model of the current running system, we can start putting them together. And the way we put them together is actually really cool. Well, I think it's cool, of course, but I'm biased. We use aspect-oriented modeling. And the most important thing for you to remember about this is that each self-function, whether it's self-healing, self-configuring, self-whatever, is captured as an aspect. And so I can actually add these different aspects one at a time or multiple into my legacy model to continuously build and upgrade it for this facade. And we do that, of course, through weaving. And so if you look at it, here's the base code. This is the self-star model. We weave that together here, and out comes the result. And of course, there's feedback so that as the legacy code changes or we add new functionality, we can keep upgrading it. So I've talked a lot about state machines. We've made a number of very significant differences, and this is part of what I'd call the overall paradigm shift. UML's good. I mean, it's being used all over the world, but in its current form, it actually isn't good enough for me to represent some of these things. And as an example, if you look at UML state machines, or Harrell charts, or Mealy-Moore machines, or on and on and on, right? Basically, a state's just a signal. It doesn't have any information attached to it. And that's kind of bad if I'm trying to orchestrate behavior, right? I mean, there's no information. I just get this plink, something happened. And so what we are doing in this project is actually redoing the UML model. We're adding in a richer definition of behavior from traditional finite automata theory, and that'll eventually get submitted back to the OMG. And so basically, what happens is the following. Imagine a device is in some initial state here, and we want to get it to a final state. So here's startup, and here's running, right? Well, in general, there's going to be a number of commands that I can apply in a particular sequence to get to that state. There's many ways to get there. I can represent that as a directed graph. Here I've made it pretty simple. And now, if I can use context-aware policy to apply a weight to the edges in the graph, I can actually force the machine to prefer a particular path. In other words, a particular set of configuration commands. And that's important because, for example, I might want to do a number of save points along this complicated configuration so that if something blows up, I don't have to start all the way back again. I can just go back to a save point and start from there. So in general, we'll have a configuration as one or more nodes with transitions between them, and if we can control the weight of these edges, we can force the particular path that we take. That's one simple application of context-aware policy. And that is represented here in the focal architecture through all these different control lines. What this means, I probably went a little too fast, sorry for that, but notice that this is an adaptive loop. Well, it's an adaptive set of loops, right? Here's my main loop, and it consists of these functional building blocks. But through the context-aware policies coming down here, through these control lines, I can change the function of that loop. I can change how, from, let's say, a simple threshold to measure to a much more complicated determination. I can change the algorithm used. I can change whatever I want in that. And so that's why the state automata are so important, because we're using UML in order to generate code dynamically, to change the state of the system, to enable it to adapt to these changing user demands and business obligations and threats, etc. So this is all about programming or orchestrating how the code that I can build at runtime can be generated to do what I want to do. And so policy is really important. This is formerly known as the policy continuum. The number, the 5 levels here, that's not really important. That's, you're going to have as many levels as your application needs. What's important are the abstractions that I'm introducing. So at the top, I've got a business view, devoid of any technical specification. At the bottom, I have an instance view. This is CF engine code, or CLI code, or SNMP code, or maybe a whole bunch, a mixture of that. And in the middle, I've got various abstractions that get me from a technologically neutral view to a technologically specific and vendor-specific view. And this slide shows, some of the transformations that take place. So John Gets Gold service, which is of course a myth, is a business policy, right? I want to end up with, let's say, CLI commands that control traffic configuration and conditioning, queuing, dropping, scheduling, etc. And so I translate John to, let's say, an IP address. I translate Gold to a set of applications that each have their own differentiated services, class of service markings. I translate those things to different functions that have to be applied inside the devices, et cetera, et cetera. Boom, out it comes. And even though this sounds really hard, we do have examples of this working in the lab. So it can be done, but as you can now see, this is really a fairly important paradigm shift than how current network management is done. We're deliberately trying to link business concepts and rules to low-level CLI or SNMP code. And so conceptually, we have the world's environment that gets filtered by policies, that gets filtered again by the particular context, and then that goes to the autonomic manager. That's how our control loop is adaptive. And the context-aware policies is here. So this slide at least caused Alva to chuckle. I don't know if he'll chuckle again. course, I can't see if he's going to chuckling, but oh well. So here are three fairly drastically different representations of knowledge. This is my life. How do I correlate this? Well, besides very carefully, I can do it in block diagram form like this. In Monday, we had a very stimulating conversation, and one of the questions that Andrew raised was, what's really important about autonomics? Well, the ability to learn and reason. So over here is machine learning, and over here is everything else. And you see those lines connecting things like modeling and ontologies and correlation and on, all to machine learning and reasoning, right? This is the essence of autonomics. Take in knowledge, use that to verify what we know, to add things if we're convinced that they're true, and all the time learn from our experience. So machine learning is really here not just to improve the system based on experience, but to gather information. If any of you were here at Mark Burgess's CF Engine BOF in CF Engine version 3, he talked about lots of different statistics that the engine would make available to the administrator. Well, that's what we're doing here. And the learning can be anything from simple data mining and correlation to some much more complicated algorithm that I'll show you in a minute. The result of these two is here. And I can't emphasize how important this is. Current network management has a static knowledge base. You know what you know, you don't know what you don't know, that's good enough, and off you go. Well, that isn't good enough if we're trying to orchestrate behavior. And so what we are deliberately trying to do in this research is to come up with a way that we can grow our knowledge base, we can lead from it knowledge that we found to be in error. We can add to it what I would call axioms, things that we found to be true, but we can't quite prove that they're true. That doesn't mean they don't belong in the knowledge base, right? And of course we can. Thank you very much. Well, at least I didn't get all the sound feedback. And I can also refine this knowledge base, make general knowledge more specific. Here's a simple example of something called reinforcement learning. And basically what it does is there's a system here, there's an agent here. The system has a set of states that are monitored by the agent. The agent takes an action, and if that action is good, the system rewards it. And so if you let the system run over a course of time, well, then the agent learns what is good behavior. Now, of course, the problem in network management is you don't want to put a reinforcement learning system on, let's say, a core router and watch it make the wrong decision, reboot it. The only thing that will do is test the efficiency of your company's switchboard when everyone calls complaining that there's no network service. So this has to be used with caution, but we can build up a knowledge base offline and then carefully, and let me reiterate again, under human control, selectively turn this on more and more to gain its advantages. Reasoning we use as really a way to form hypotheses. So in comes my SNMP critical alarm. What caused it? It probably just didn't fall over because it had nothing else to do. There must have been some root cause there. And so the machine-based reasoning can hypothesize one or more causes, and then it can direct the system to go gather data to either verify or falsify those hypotheses. And guess what? All that goes into the knowledge base as well, so that the next time that happens, or a problem similar to it happens, the machine can suggest to the human, why don't you look here or here or here, because I think it's such and such. And both of those are used to do what I call semantic reasoning. So on the left here is one vendor's device with a set of commands, and on the right here is another vendor's device with another set of commands. If I want a service to run, and here's my favorite word in the whole wide world besides guaranteed, which is end-to-end, then that means that you and me, the administrators, have to know, where did it go? There it is. This language, and more importantly, we got to know which commands from this guy equal which commands from this guy. Up here we see 1.0 and 0.95. That means that this set of commands here almost but don't quite match the semantics of these. If any of you are interested in how we do that, this is a fairly long discussion based upon modeling and first-order logic, but it's done, it's working, yay, hooray. And machine learning is really hard. This is a chart which I encourage you to look at when the PDFs come out, not necessarily here. Basically, you have a number of learning models on the columns and a number of characteristics that you want to use on the rows. And basically, you've got a matrix that says, well, there isn't one good choice for any of these. In fact, there aren't even two good choices. There's a whole lot of them. So machine learning in our system isn't just one algorithm. It's a set of algorithms, and we need intelligence to select which algorithm or algorithms to use based upon what? Based upon context. So to illustrate that, here's a simple example. A BTS is basically a base station that controls a bunch of mobiles, and we want to do predictive analysis to see when it's going to have a failure. So down here are two different types of neural networks. The one on the left is formally called a multi-level perceptron. The one on the right is an RBF, or a radial basis function type of learner. Big deal. The importance in this is that they're completely, totally different. The RBF, for example, uses both supervised and unsupervised learning, which the perceptron doesn't. And so the problem then is that if I, whoops, come back here, is that I don't have a single choice that always works. So here, if the heavy black line is the real input function, if I look at it from a global point of view, using the multi-level perceptron, I get one behavior, see this tailing off here, whereas if I use the RBF function, it does really, really good, and then it misses. And I could show you a whole bunch of other graphs that have completely different results based on whether there's outliers. In other words, let's say I have a big Gaussian peak here, and then I might have a couple smaller peaks down there. Some machine learning models will match the big peak and completely ignore the outlying data, whereas others will try and average through that. Which one is better? Well, it depends on your context, right? If you use them offline and you give them sufficient time, well, they'll be pretty much the same. But if you use them online in real time, then the multi-level perceptron is less sensitive to change, whereas the RBF is much more sensitive change because of its use of unsupervised learning. So, in summary, one last sound clip to leave you all with. It's not just about technology, right? So, there's my dear wife. You know, that would be the one that called me the moron, remember? And all of a sudden, which is, of course, clearly my fault if you've been in the Strassner family household. And so, you know, she gets on the phone and calls the service provider, who, of course, sends out the technician who says, "What the hell is UML?" Right? So we got to do better than just having really cool conference papers and, you know, papers with lots of equations and stuff. We actually got to build this stuff, which is what my lab is all about. And if you look at any service provider, and this slide is especially for a particular person, Andrew, right? What looks simple is usually not so simple. And yeah, that's actually a real wiring closet, again, name withheld to protect the guilty party. And so here, where is this person? Oh, it's right here, this jack, XJ4_7721. Naturally, right? So again, there's a ton of complexity, whether it's physical cabling or software or other things. Autonomics is a paradigm shift that tries to overcome this. Now, a man much wiser than me, Einstein, said everything should be as simple as possible, but not simpler. And that's the case with autonomics. If you want something life-changing, like self-configuration, you're going to have to put in the work. And yeah, it's going to be complicated, right? It's not going to be easy, but if you put in the work, then you should be able to get the results. In this case, the results are done through the embracing of software and tools that don't replace the human, rather they help the human do their task. And of course, if none of this has convinced you that autonomics is really good, well then, just out of my 12-step program, it's good enough, it's smart enough, and doggone it, people like it. So, with that, thank you very much. You've been a really attentive audience. At least I didn't hear any snoring. Of course, I couldn't see you if I did. And I guess flood me with questions. I probably shouldn't have said that, so thanks. I know Andrew's got to have about 422 questions, so you might want to get up to the mic before Andrew gets there. None? It was, uh-oh. So now we need to break to scary music, you know, do, 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 do.
I have a question.
Please.
I don't often have a favorite slide, but my favorite slide was number 40. I'm sure you remember which number 40 was.
Sure.
It's very interesting work. It's fascinating and very promising. I just need more specifics.
Okay.
And 40 was my favorite because there was a lot of, you talked about what you're actually doing. Can you talk more about what you've actually implemented? Not necessarily in this level of detail, but in more specific.
Sure, sure.
Thanks.
So what we've done, this presentation showed a number of parallel research efforts that are going on in my labs. Our first problem was to prove out the machine-based translation, because this whole nonsense of most networks are configured using CLI, but command line interface, but monitored using SNMP. And the problem with that is there is no RFC that maps between the two, right? And so what we wanted to do was to say, okay, one of the foundations of autonomics is this ability to have a global lingua franca. Now that does not, not mean that we go out to the Ciscos and Junipers and everybody else and say, hello, change your language to this. That's got as much chance of happening as, well, me finding my glasses right now, which is 0. What we do is we build a language that can map those different vendors to our language. And that language we're actually standardizing, by the way, so it's not some proprietary thingamajigger, right? And it's because what we really need is the standardized representation of the management data. We can argue until the cows come home as to whether one language is better or not. I'm personally still shocked by the number of Visual Basic programmers out there, but you know, I come from a small talk and Eiffel type of programming background, so I think you can see why. But I mean, we're never going to have one programming language, right? But if we don't have one way to represent management data, frankly, forgive my French, we're screwed. So we've gone out and built a couple of translations that take Cisco iOS, very different versions of Cisco iOS. We model the functionality of the command, both syntax and semantics, in UML. We translate the UML to this lingua franca. We then translate that back to SNMP, and that's how we map that data. So that was one. What else have we done? We're starting to extend state machines. We're building some software that actually modifies the state machines that you have in UML and SDL. That's kind of a work in progress. At the application layer, one of the things that was really cool, solving a real world problem, was this. Service provider, you know, name withheld to protect the guilty. When they got a new board for their router, it took them about 30 to 45 days to instrument it, install it, and bill services on it. That's a whole lot of revenue lost, all right? So we wrote some software. Oh God, anyone but Mark, please run. Well, except Alva, I guess, but back to your question. So we took,
Careful what you ask.
aww. Yeah, you know, so we took our software and we modeled what different types of configuration options that we could do. We called them configurates, which I thought was, you know, a brilliant entering into the marketing domain from me. And we built these as a set of libraries. And so then we instrumented the, in this case, Cisco routers as, so anytime an online operation happened, card insertion, card removal, et cetera, it would send a syslog event. Well, cool, right? So we trap the syslog event, parse it, figure out who sent it, talk to the router in native iOS, because over a remote line, it's about 1,000% more efficient than talking SNMP. I mean, I can just do a show tech, for example, and boom, you know, everything that I need comes out. So then we used a parser, a factory pattern to build a set of parsers. So for one, because Cisco brilliantly has different formats and different data for the same show tech command for different products. Welcome to my life, right? So we build this parser factory, and you know, that way, you know, there's some things in iOS that have never changed since Chambers was a baby, you know, like BGP, autonomous system number, you know, blah, 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 right? So, and then there's other things that change on a version by version basis. So we build parsers that start with Cisco versus, let's say, Motorola, and then keep on factoring till we get to the right version. Once we figured that out, we then installed the correct parameterized code, installed it, verified it. Again, we've got our control loop there, right? Signaled the sysadmin, we're ready to go. The sysadmin did his check, and we reduced, you know, the time from 30 to 45 days to about, you know, 5 minutes. ROI 5 billion trillion %, and we were heroes. And then they put it into a production network, to my horror, but it actually still worked, thank God. So.
Great, that's helpful, thanks.
Anyone else?
John, sir, thank you.
Yes, Mark.
Thanks for a great, entertaining and stimulating talk. I just wanted to go back to the very first slide, where you showed this operational support system, business support system.
Okay, my very first slide.
All right, then, clever plugs.
I'll pay for that
The
later,
second
but at least I got the first blow in.
The thing that looks like the Borg cube, yeah, this thing.
Yes.
So, how does autonomics actually help us to simplify this? Can you say something about how all of this technology will help to simplify the problem that you highlighted here?
That's actually a really good question, Mark. So there's a number of problems in this Borg cube operational support system. The first is just the stovepipe nature of the cube. In other words, you know, I've got the blue admins doing one thing and the red admins doing another thing, and they don't really talk to each other. So what we're doing in this research, and actually my answer to Eileen, I think is kind of applicable here, by building common knowledge representations, we're able to start building bridges, if you will, between the blue admins and the red admins and the yellow admins, et cetera, et cetera. More importantly than that, as you know, autonomics is about abstraction. Remember the policy continuum, right? Business up here, no technical details. Implementation down here, no business details. And levels in between to translate them. So what we need, the first thing that we need to do besides having a common knowledge representation is to be able to translate what these different admins are really trying to do into a set of common forms. Okay. In terms of automation, right, I mean, that answer is obvious. We're now starting to get a line. Is that who I think it is? Oh, God. So maybe I should keep on droning on your question, but so let me stop there, and yes, I'm ready for my pounding. Alva, you want to go first?
Okay. Well, first of all, you've shown us two ontologies that we do together. One of those ontologies is the ontology of business process, and the other is the ontology of machines themselves. I claim that most people in this audience are more familiar with the third ontology, which is the ontology of self-protection. Now, it seems to me that the average system administrator is a pretty good autonomic element in the sense that they react very strongly to do this or this happens and you're fired. Furthermore, that
works for me too.
that policy is not part of the two ontologies you're talking about right now. To get this adopted, I think you have to protect the human being as well. And I'm wondering if you have any thoughts on how your system might actually code a rule, don't do this or I get fired.
That's actually a great question. Humorously, we have thought about that because of exactly what you just said. If I've got this highfalutin system, software that comes out that claims to automate everything and make your life wonderful, and you trust me and then get bitten by it, I'm dead. That's not a good position to be in. So not only are there policies at each level of the continuum, there's what we call these safety policies, right? And I lost my, shyness about, 30 or 40 years ago, and I encoded that into the software that we're building. So if we see something that just doesn't add up with the current environment, I mean, we, throw up dialogues, we, print out logs, we do the normal things that you would expect that says, you sure you really want to do this? And so that's a good question. I think that's actually an often overlooked point, right? You can use learning and reasoning not just to solve a problem, what's the root cause of this alarm, but also to protect yourself. So very good question.
Yes, my question was, as you're going through this whole process, it almost sounds like you're designing top-down and then implementing bottom-up. Is that true? And then as you keep kind of circling around it, do you continue to, okay, well, we got this far, let's reevaluate top-down, implement bottom-up? Is that the process that you're all continuously going through, or does it change?
So that's another good question. Kind of yes and no. There's some things, like especially business things, that are just inherently easier to analyze and work in a top-down fashion. There's other things, like, the network did what? That we didn't expect, where it's much easier to work in a bottom-up fashion. So the way that I would really answer that is another characteristic of autonomics is it's a programmable tool set, okay? It gives you the ability to work top-down or bottom-up. Definitely in the development and debug process, we definitely iterate, top-down, bottom-up. It certainly isn't a waterfall type of model. But, I think what's important is to enable the developers to work in their own way. I mean, who am I to tell you how to architect your system, right? And so that's why we're trying to give you a set of tools. If you want to go top-down, go for it. If you want to go bottom-up, go for it.
Thank you.
Hot row.
Good morning, John.
Oh, that can't be good. But good morning, Andrew.
Let's try and marry this slide to the title of your talk. My experience with this sort of architectural mess is that quite often you get systems that are antagonistic to each other. And in fact, this is exactly the problem with HAL, was that in fact had two conflicting directives. So I'm wondering about the general issue that you have when, particularly as you try to apply learning, what happens when there actually are disjoint parts of the system that actively have contrary goals? And how do you do that resolution? It's not like policy conflict resolution, although I don't see that in there either. But when each sort of sub-part of the system actively wants to hurt the other part or somehow destroy it or just upset it.
Let's see. That is I think in order to answer that question, we'd be here for about an hour. But let me take a shot at it because it's a really important thing. What I've tried to do is, in this architecture, this high-level architecture, where we started with context determining a working set of policies, which then determines functionality, right? In theory, the policies would all be coordinated, and you shouldn't have that. Now, in reality, you and I both know that you're going to have conflicts. I mean, a simple one, Andrew gets gold service, FTP gets bronze service. What happens when Andrew sends FTP, right? So, not shown in here is a fairly large body of work on conflict detection and resolution. I can give you a whole bunch of papers, and soon we should have a SourceForge site where you can download a policy engine and play for it.
Where does it fit architecturally in this diagram?
Architecturally, policy manager here, it sits in here.
Okay.
Policy manager actually blows up into a full-blown engine that has policy authoring and editing tools, policy verification tools, policy conflict detection tools, policy resolution tools, and then brokering, right? Because
what if it's not the formal policies that are in conflict, but the observed behaviors?
Then that should be handled by the particular learning and reasoning algorithms that we've got. Okay. Well, I guess that did good. So.
Hi, my name is Christian Bauernfein. I want to thank you for an interesting glimpse of the future. My question is, it occurs to me that the more autonomous those systems get and the more intelligent they get about managing themselves, the more they will also become a black box that is very hard for us to understand and to fix if and when they will eventually break. So is self-documentation somewhere in your picture as one of the big four selves?
You know, I knew I should have kept that slide. Actually, it is. So the reason we have an actually interesting take on model-driven architecture, go to omg.org/MDA, and you can read about it. When we generate code, we actually generate documentation for that code, and we do this especially for all the tools so that other people can use the tools to, do their own type of MDA approaches. I'm not going to sit here in front of you and lie and say the code, the documentation is perfect and we haven't, but I mean, at least we try.
Well, that is documenting tools, but how about documenting processes? I mean, I don't know, I'm not a lawyer, but SOX may not allow me to run a system that defines its own processes that I can document.
That one I'm not sure, to be honest. So far, what we're using, I mean, our development environment is Eclipse-based. We're trying to use open source. We're going to be contributing a whole bunch to open source. And so, in theory, the standard rules and regulations that you would have with any open source project should apply. Before we upload things, I mean, I'm sure I'm going to get visited by a whole bank of lawyers, that are going to say, well, you missed this, and you have to add that, and whatever. But that's the theory.
Thank you.
Mm-hmm.
Okay. I'm mentioning another human component here. As we gain many of the benefits and cost savings in this model, I'm concerned that you remove the whole developmental strata for future admins. As you relieve most of us of the mundane duties and we do more engineering, architecture, deeper problem solving, how do you develop a next generation of admin? Because often some of those lower level tasks that you're automating are how they cut their teeth before they're ready for the more difficult tasks.
So great question. My answer is the tools that we're developing are there to help you continue to cut your teeth on, your own exploration. I mean, we can't, by any stretch of the word, anticipate every single problem that's going to go wrong, right? So what we can do is we can build tools that will automate the gathering and collection of data, we can make those tools extensible. So if you want to collect different, data types or different file extensions or different, other types of data that we don't have, our tools better be able to be modified by you so that you can do that. The processes by which we analyze, we've chosen one set of algorithms, but the whole purpose of my set of slides on reinforcement learning is to say, there's no set of algorithms that I could give to any of you that I could say would always work for all network applications. And so what we'll do is we'll instrument a couple common ones, and then I would expect an open source community to form saying, well, let's try this other one. Does that help?